three talks. So really, I just ended up with a job of discussing the models the next three talks will then talk about in detail. And therefore, we have a whole load of people who have done various bits of work on these various three models at various points in time. But before I do that, I have an announcement of two upcoming workshops. One of them is less organised, and one of them is more organised in the sort of wrong order. So the one which is more organised is one next year. So firstly, there will be a one-day meeting in London at the RSS in Errol Street, organised by the RSS Applied Probability section on energy, probability and statistics. The date is not confirmed yet. The location is, but that's all that's confirmed for that one. Looking further ahead, there will be a 3-day workshop in Warwick in April 2014. We have dates, from the 14th to the 16th of April. Very shortly, there will be a call for papers for that, and there will be a mixture of invited and submitted papers at that meeting. So I hope to see you all at those two meetings. Okay, so as I say, in some sense, this is now going to be a talk which is really an introduction to the next three talks, where I'm going to basically introduce the models that they're looking at, and it will give you some motivation between these models, and then I'm going to leave it either to the PhD students or Stan to then talk about what we know about these models and what we can say about them. So all the hard questions should be saved for later and not given to me. Okay, so we've seen these sort of slides already. We know we're moving to a low-carbon future. We know the world is changing. We know generation is changing. We know we're going to have much higher renewable penetration on the network. And this is going to bring with it lots of issues, but two of the big ones for us are variability and uncertainty. And this is going to cause an increase in operating costs. So the question is, can we model these? Can we gain insights from some simplistic models, which will then feed back to help us understand how to reduce these costs and not have such a big problem as we go ahead. So what we're aiming to do is we're aiming to look for so hopefully you'll see these are really quite simple models which try and capture something about what's going on. They're not going to be realistic in any way, shape or form, but I hope to give us some qualitative insight as to what's going on and the behavior, and understand some of the sort of statistical properties which are important for the systems, things we should be trying to understand better. So things which sort of questions we're trying to look at answering here are understanding the value of storage, understanding what sort of statistical properties you want errors for the wind forecast to look like, what are bad errors, what are good errors, how do we deal with unseen effects of seeing errors we know are coming, but we don't quite know how big they're going to be or when exactly they're going to come up. So I'm going to look at three models. I'm in the sort of wrong order for the talks, but each one really relates to one of the talks coming after me. So the first one is going to be a very simple model, which actually you've seen most of it already, because Jean-Yves gave a fairly comprehensive talk about this. But we've been looking at it from a slightly different perspective, and we're also starting about some of the extensions beyond what he did. So in a many sense, that model you've seen before, but I will go through that one in quite a bit of detail as well, and also talk about a slightly different perspective on demand shifting, how demand shifting might fit into that modeling framework. Then I'm going to look at a question about so that's using storage in some sense for reducing reserve setting and excess conventional generation. Another use of storage, which is often touted as one of the main values of storage, will be in arbitrage. So can we start to get a feel for what the value of storage in arbitrage is going to be? We're going to take a very simplistic view. We're going to assume that we're God, we know everything, and we're going to run our store the best we can and try and understand what the policy looks like to run the store, and then start backing off full knowledge. And then finally, if we know something's going to change in the future, we know there's going to be a change in the sort of setup. So for example, a frontal system is going to come across the UK, but we're not sure exactly when it's going to come, exactly how big a change it's going to bring with it. How should we be looking to ramp our conventional generation either up or down at that time to deal with that change, to minimize our costs? Okay, so I'm going to look at these three. I'll look at storage for balance, and then storage for arbitrage, and then finally minimizing cost errors. So storage for balance. So what we're looking at developing a sort of framework to study storage in terms of balance, and also then think about the issue of, can dynamic demand fit naturally into this sort of framework? Is dynamic demand, in some sense, for these purposes, just the flip coin of storage when we look at these sort of simple models? And one of the sort of driving questions that I've sort of been interested in is we know, okay, we talk about wind data. We know we don't have enough wind data in many circumstances. So if we're going to create fake wind data, can we understand from these simple models what statistical properties for fake data really should be doing well? Because no fake data will do everything well. So can we understand what the fake data should be trying to do as well as it can? And for this talk, I'm going to be thinking about transmission networks and associated issues, none of the DNO stuff that we saw yesterday. But there's lots of interesting problems there, and I'm sure lots of interesting talks from that perspective later on. And it's very simple models. So as very similar to Jean-Yves' simple model, these are going to be very simple models. We'll start with single stores and build up from there. So, as I said, I'm going to be quite open that I'm ignoring lots. And here are some of them, and I'm sure there are many more, and I'm sure that the engineers will tell me I've ignored huge amounts as well without realizing it. But things which are often talked about which we're ignoring are reactive and active power, ignoring all the market mechanisms, ignoring all the policy, and ignoring any variation in conventional fleet. So the setting that we're going to be thinking about this particular model in is in stochastic dynamic programming. So we're going to be doing this in discrete time. So each time the operator has to make decisions. So it's going to decide how to schedule conventional plants, how to utilize pump storage, and then how much curtailment of the wind generation should be carried out. And what we're really looking here is to minimize cost. And what we're doing is we're looking to minimize cost subject to keeping the lights on. And it turns out that rather than power, we should think about energy. It's a much more natural sort of setting for these sorts of problems. So given we're thinking about stochastic dynamic programming, what is our constraint going to be? So the aim is to keep the UK powered. How to do that? How are we going to model that? So a hard constraint is not applicable. There are always going to be a chance that you won't do it. So instead of a hard constraint, what we've done is we've gone and we're looking at a probabilistic constraint. So what we're saying is that an admissible policy for these will be such that the probability of failure is less than some given probability. So that's what we're looking at in terms of what an admissible policy is going to be in this setting. So now we want to think about cost. So our cost here, dealing with money is hard. You have real-time energy markets, you have bid-offer processes, you have all sorts of complexities coming in. So let's pretend we're not going to deal with money itself, but instead minimize lost energy as a proxy for money. So we're going to be looking at minimizing lost energy in two ways. One, through spilt generation, and the other through storage cost. So this should be thought of as the efficiency of a storage system. And we're looking to minimize the long-run average lost energy per period. So now, we've got our cost, we've got our constraint what makes misfills, so we now need to put in our generation. So conventional generation is slow. And this is, in some sense, this is driving all three of these models. And you can see this is slow often in two regards. One is there's a ramp constraint, or there's a control lag. So in this model, reality is somewhere between two, and both of them really apply in reality. For this model, we're going to ignore the ramp constraint at the moment. That will come back in as we move along this work. But what we're going to be doing it is via a control lag. So what we have is for our conventional plant, you have to schedule its generation some number of time periods in advance. So then our storage. So we think of storage, and here we're going to think of storage being quantified by three parameters. The capacity of the store, the rate constraint, so the amount you can put in and out in each time period, and then the efficiency of the store. So either through moving in and out, or through leakage in the store. So then we need some notation. So AJT is going to be the amount of energy in and out of a store at time t. And then we're going to basically doing, so for those who've spent time around queuing theory and these things, this is just a double score-hold reflection. What you do is you basically look at taking the value, the amount of you have in store, adding on what you're adding in or out, and then losing a bit for efficiency. And then you have a max amount, and you can't ever go below 0. So we've got conventional, we've got our store, so finally we have our demand. We have a net demand process. So we're thinking here, so pretty much for everything I'm doing here, I'm thinking about net demand, so that's actual demand minus wind generation. And that's where our stochastic process is coming in. We'll assume it's a stationary stochastic process. And then we have distributions for this. So we don't know what exactly it is, but we have a distribution for this, and we make use of that distribution in making our future decisions. So this is probably in some sense what I've done already is all sort of less controversial. It's what Jean-Yves did. This one is sort of a one which is slightly different to Jean-Yves, which is now saying, actually, in some sense, this whole modeling setup for storage, dynamic demand can be thought of through, you have to squint your eyes a little bit, and thought of as being very similar. So what dynamic storage is moving generation through time on the sort of supply side, whereas storage is moving demand through time on the demand side. And again, for a demand response system, you have an amount, a rating you can put in and out. So this is the maximum power that you could shift at any point in time. The amount of energy that you can shift. There is a gain. You can be thought of as a leakage, or in the case, as Jean-Yves said, you can think you might need extra energy to compensate for the demand you've shifted through time. So in many ways, a demand is going to look very much, a demand shifting is going to look very much like just another storage system of a system, and you can be quantifying it in the same sort of triple set of parameters as we've been doing for the storage system. But we now have one issue that we didn't have with storage. So storage, if I put a piece of energy into storage, I sort of don't care when I take it out again. But with demand shifting, there's a time limit. So we have to think carefully, and this is still very open, and there are still issues to be thought about here, and we don't quite know exactly, have a formulation quite right, we think. But there's a time issue, and there's only so long you can keep things in demand shifting. So this is saying, I think we can put demand shifting into this framework very easily. I think it fits, but there is some issue still to be carried on there. Okay, so now you've set up a vague, sort of quite general framework. What do you do first? You go with a simple model. You look at a single store, one single conventional thermal plant, and a single demand. And then you also make it even easier. You go for 100% efficiency. You don't put any input-output rate constraints, and you have a single capacity store. So that simple model is what Glyn will mainly be talking about later. He will talk about some more bells and whistles on it than that, but that's where we started. And now the next couple of slides will be where we would like to go. So we don't have any results for the next couple of slides. We don't know what's going on there, but I think they're the sort of next steps you naturally take with these models, and the natural models we want to think about next. So the first one is you just add a second store. So you keep everything the same, but you add a second store. And now you really are looking at the case where, in some cases, so why do you think about second stores? Because you now might think of a situation where you have a very large store where the rate in and out is relatively small. So I think de Norwick or such like. And then you might have a second store which is much, much smaller, but its rate is much, much larger. So here you're thinking of dynamic demand, where you can do something, you can do a lot very quickly, but you can only do a small amount of energy shifting in that case. So how do you play the two against each other? How are they useful to be played against each other? So that's the first case. and then you add a link. So now you start adding spatial, you add two demands, you add two conventionals, and you add a link, and you start to see how do we play these across the link. If the link has a single finite capacity, because we only have a link, we don't have to worry about Kirchhoff's laws or anything like this, but it does at least start to get some sort of spatial issues going on there. At the two extremes, you can see that if you have the link capacity is 0, then really this is just two separate systems. If the link capacity is infinity, it then degrades into the same system we saw before with just two stores. So how does varying this link give you extra benefit in terms of cost? In terms of cost reduction for the system? Is there going to be, how does it move smoothly as I change the size of this link? And you can think of this sort of situation being a quick model for things like what happens if you put storage in Scotland and storage in England, and you have a finite capacity between the two, which we've heard already this week exists, and we have these problems with wind in Scotland and not being able to get all the wind into England. Okay, so that's sort of our first model. That's what Glyn will talk about later. So now we move on to our second model, which is storage for arbitrage. This was a sort of, came out of discussion with Janusz, Frank, Richard, Stan, and I, and Chris, about can we get some sense and capture, in some sense, and understand what the value of storage in an arbitrage market are, where we're going to start by assuming we're God, and saying, if I'm going to run this store as best as I can, what would I do? How would I be running it? How do certain constraints on the size of the store and the power flow of that store affect what's going on? So we start by assuming no randomness. We just know we have an entire just an entire trace of demand. How should we let's take the simplistic view and say, how should I be then taking that and then turning it into making money on arbitrage? So we're going to start, as before, we have a very simple thing, but we're going to be really concentrating on this relationship between E and P. So E is going to be the size of a store, and P, then the input rate, output rate constraint of a store. So really the questions we want to try and understand is here, how does the policy change in terms of this ratio E and P? So when you start thinking about it for a little while, you realize that it's the ratio you really care about. So we thought and we then realized actually we'll start doing this. We started doing this in the case where you assume that you don't affect prices, but then we realized fairly not long after that actually you can do everything where you do have your market effect in prices. So rather than having a price curve, you have a demand curve, and then you have a demand to price curve. Oh, again, it's net demand. It's demand minus wind that we're thinking about here. So this price curve is the cost function is really the cost function for your conventional fleet again. So we've seen, Pierre showed us one of these earlier. So now we have impact on the market, and all we're doing is we take our demand, we decide how much we're going to add or subtract that demand by pumping in or out of a store, and then we can get a cost out of it. And then you can then start thinking about what is the dynamic programming problem you want to solve here. Here it is. I'm going to leave the explanation of this up to Stan mainly, but really just to preface what he'll say later, is that it all comes down to timescales in some sense. There's different, depending on the ratio of P and E, you'll get different timescales that you'll be interested and care about. And that's where sort of the interest comes. And now we have a fairly good idea of what the policy should look like. And now we're trying to, so now we have a good sense of policy looks like, where we're going with this. Let's give you some feel for what we're looking at in the future. We're looking to see what happens now if I start relaxing this full knowledge assumption. So what happens if I'm starting to run these timescales? I know what sort of timescales I should be looking at. As I relax the full knowledge assumptions, how do I lose on the arbitrage? Where is there less money to be made? Equally as well, in some sense, what we've done is we've said, let's take, there's a map now from this curve plus P and E, true to a real number, which is the value of the store in arbitrage. We, in some sense, concentrated on what the mapping associated with P and E is. Now let's try and understand what the mapping associated with this curve is. As I make this curve burstier, as I increase the number of frequencies of up and down bits, the size of them, how does the value change in that case? How can we understand this associated map better? And what do our insights about what the policy look like tell us about what this map looks like, and try and understand it. For example, if we now pretend that everything is nice in the world and assume that demand is sinusoidal, how does the value of the store change as I change the frequency of that sinusoidal wave? Okay, so now the final one. So this is a model which partly came out of discussion with Anu Richards. Sergey is working on it with Ksenia, who's another one of our PhD students at Heriot-Watt. And this one I'll talk about least. So we have errors in our system. Small errors can be dealt with quite easily by fast response, but much errors require more drastic action. We've said, as I've said many times in this talk and throughout this week, conventional generation is slow. If you have one of these errors coming, you know there might be an error coming, so the sort of, when I'm thinking about this problem, I keep in the background of my mind a frontal system passing across the UK. You know it's coming. You can't quite predict exactly when it's coming. You can't quite predict exactly how big the jump will be. How are you going to be ramping your conventional generation to deal with that, to minimize the effect of that sudden change in the way the system behaves? So if you're going to use conventional generation to deal with this error, you have to do something preemptive. So what preemptive action should you be taking? If you fail to preempt fully, you still have to keep the generation on, so you have to go either to your fast reacting plants or your interconnectors or somewhere where it's very expensive to get the power from very at short notice. So just to give you some sense of what I'm talking about, so this is a plot, this is some data that we got from Andrew. I stole from Ksenia's slides. This is the errors, predicted wind error data. These are the errors. So there's lots of errors, but really what we're wanting to do is we're wanting to say, actually let's strip out a lot of the small errors, let's just assume they can be dealt with elsewhere. And then what you get is something like this, where you see sort of, to people who have spent time around sort of processes, what you see here is what looks like a point process marked with sudden errors. So what we're really thinking about here is modeling this with a marked point process. Simplicity, we're going to work in continuous time. Results really should carry across in both cases. So our error is really going to be a marked point process with shock errors. And we're going to have two costs, the cost of failing to cover our error, so that will be what we need to spend our expensive generation on, or a cost from this ramping of conventional generation when we don't necessarily need it. And what we really wanted to do is we're wanting to minimize the long run average cost. So what we have is we now have a conventional generation. We put in some ramp constraints. The ramp constraints here we're just going to assume is going to be on the first derivative of the amount we can provide for conventional. And then we have these two costs, a C1, which is going to be the cost for failing to meet our error, and our cost C2, which is the excessive conventional generation that we're going to need. So for more details about that, see the talk by Ksenia later. She will talk about what happens as we look at various cases for this point process. So she'll start by thinking about deterministic point processes and then moving on to some more interesting cases. Okay, so I think that's all I have to say.
I'm sure we're all looking forward to these three talks. Are there any questions from now, James? If not, then I'll let us all go to coffee and we end at 11:30.